And we're back for part 2 of video 1. Who would have thought it'd be multiple parts? So, we're looking at the study guide and exercises 1 through 5, where we see 5 different tables. Now, the essential questions we're dealing with, we're going to be tackling them kind of in parts. First one, how is a linear function graphed from a table of values, obviously, as we're given? And then next, how is a linear function rule written from a table of values here? So we'll be dealing with other things here in a second. So we're going to look at the first table. Now the first thing that we always want to look at whenever I give you a question like this, the first thing I might ask you is it a function? So you're going to want to look at the input values of x and make sure that each input has exactly one output. Virtually you're looking for, do I see any repetition in the table here? So I see all of these numbers are unique to one another. I don't see anything repeated. So I'm pretty darn confident that this is a function. If I wanted to, throw you off and say, is it a function or not a function? I could throw something like 5, 212 on here. Now all of a sudden this relation is not a function any longer, because if I put a 5 in the function machine, the machine doesn't know which output to give me. Do you want the 13 or the 212? Function machine isn't smart enough to know what we want. So this would not be a function. But we're going to deal with it being a function as it is. And in fact, all 5 of these are functions. So the first thing we want to look at is it a linear function? So we're looking at that delta y over delta x thing. So we're going to examine what is the change in the input values. So I'm going from -3 to -1, that's an increase of 2. I'm going from -1 to +1, again an increase of 2. From 1 to 3, I'm noticing a pattern that all of these input values are increasing by 2. This is not necessary for a linear function. I could have all different increases. What's going to matter is the ratio of the change in y versus that change in x. Just so happens that every denominator I'm going to write over here will be 2, as the change in x was constant. Now I want to know, is the ratio between both changes constant? So going from 1 to 4, an increase of 3. From 4 to 7, again an increase of 3. From 7 to 10, things are looking good. Now if this change was anything other than an increase of 3, which it is, this would not be a linear function. But it just so happens that all of these changes were constant. Not only were they constant, but I have to look at each 4. You see how I have 4 different changes? I have 5 points that are represented. Each of these are ordered pairs. I have 5 ordered pairs that represent 4 different changes. It just so happens that all of them not only were equal to one another, but happen to be exactly the same value. So this is linear, meaning that not only is there a constant rate of change, which is 3 over 2, if I graph them, I would find a line. So let's do that. I need to get from -3 to +5 on the x-axis and from 1 to 13 on the y-axis. I don't need any negative y values. So I'm going to not really represent the 3rd and 4th quadrant all that well, because I need to get high up here in a limited amount of space. Now I need to get from -3 up to +5. And I need to get all the way up to 13. Notice that these spaces on the x-axis are a bit wider than those on the y-axis. That's fine. What I need to have happen is all of these be constantly spaced against one another. Now again, we're just sketching here, but I can't have very obvious. I wouldn't want to have something in the middle there that would represent a full jump when the last jump was that wide. All of these need to be fairly well spaced equally, and all of these need to be well spaced equally, but they don't necessarily have to be the same scale. Okay, so when I put these on the graph, we should see, if I were to connect the dots, I should see a line emerge. So I have the ordered pair, -3, 1. So -3, 1. The ordered pair -1, 4. 1, 2, 3, 4. So as x increased by 2, y increased by 3. And then I have the order pair 1, comma 7. So 1, 2, 3, 4, 5, 6, 7 right here. Right now things are seeming to line up pretty good. Even with the sketch, now I'm at 3, comma 10. So I'm going to skip over the x value of 2, go to 3. Notice I haven't numbered anything. That's fine. If I was to, have each of these representing a 5, 10, 15, 20, a jump of 5, I would definitely want to label them. These are all just singular units, so it's fine to say 3, comma 10 will be 2, 3, 4, 5, 6, 7, 8, 9, 10 over here, right about here, falling right in line with what we have. And the final point, 5, comma 13, right about there. Now, with the information that I have right now, you might be like, cool, connect them. With the information I have right now, I have no reason to connect these dots. That's something we're going to talk about in video 2, when to connect or not connect dots. That's the difference between two different types of functions. Right now we have one adjective to describe a function. It's either linear or nonlinear. We're going to have a couple more adjectives before we're done with this. So for right now, I'm done. Okay, let's move on to the next one. We might come back to this, we might not. We'll see where the day takes us. Hey, all these input values seem quite familiar. These are all the same input values from exercise 1. Hey, this looks very familiar too. An increase of 3, an increase of 3, an increase of hey, that's only an increase of 1. So I notice that the delta y over delta x ratio is constant for the first 3 changes, but then I find that the last one is not constant. So this is nonlinear. It has to be constant for the entirety of the function that I know about. So it being good 3/4 of the way through is not good enough to make it linear. And if we don't have to sketch this whole graph, but we can look back at the last one, we saw a line emerge here as I start to connect them, as I said I shouldn't. You saw a line appear here, and all of the points were the same except for this one, 511. Now where would 511 be on this graph? This was 310, so 511 would be right there. That dot does not lie on the line that we've been making. That's why it's not a line. To go from here to here to here to there, that's not a single line. It's kind of like what we saw in the previous video on the last page, where we had points that, if I connected them, seemingly made 4 lines. If I'm talking about a linear function, I'm talking about a singular straight line, to be redundant. Okay, so far so good. Let's look at table number 3. What's this guy doing? So we have some different inputs, so we'll need to take a look at that. Oh, it's the Fab 5, -2 to +2. So we have increases of 1 everywhere. Good time. Now let's look at the delta y values. You might notice, and it's always a good thing to notice when looking at a table, that in the previous 2 examples, as x got bigger, y got bigger, and we saw an increasing value represented on the graph. Even when it wasn't linear, going from this value of 3, 10 to 5, 11 still showed an increase. I notice now I'm starting out at -210. My y values are getting smaller here. So when I draw this graph, it's going to represent a decreasing function. So here I have a delta y over delta x of -3 over +1. So if this was linear, the next thing would have to be the exact same ratio. Oh, no. I know right away this isn't linear. But I wasn't asking anything specific. I'm just messing around here. So to go from 1 to -8, that's that. And to go from 8 to 10, that's that. So this is certainly a nonlinear function. But as some of you have remarked in class, a pattern still seems to be there. If we're looking at the rate of change of the rate of change, I see something happen. After I do this twice, I get something that is constant. Now that doesn't make this linear. I have to find it being linear on the first go. what I'm doing here is something called successive differences. And this is something that if you take finite, we'll talk a lot about as we deal a lot with sequences. Successive differences is what I'm doing to kind of find the rate of change. I'm finding the difference in these values successively, so it kind of makes sense. To do this twice, and we did this together in class, I know that this is not linear. Linear being a first degree equation. I know that this is actually a second degree equation. This is a quadratic function, which is something that we're going to talk more about once we all decide to come back to school and stuff like that. So I know that this is certainly nonlinear, and with a little bit more formal instruction, I'm going to know that it's actually quadratic, which means that, as we saw on some of the things that I've done with Desmos in class, this is going to make a graph of a curve called a parabola. But that's something we'll deal with shortly. Now, if we were to graph this, let's see what it looks like by hand. Now I'm going to kind of come up here and borrow some space. I need to go from -2 to +2, but then I need to go from 10 to -20. Sheesh. So from 2 to -2, I need to get all the way down to -20. So I need space in all quadrants. I'm going to have to make this pretty tight here. $18. Okay, so that's -20. We need to get up to 10. Okay, and I only need to go from -2 to +2. So you can really see in this graph how I was saying the scaling doesn't need to be the same. I've got much wider x values than I do y values. That's fine. So at -2, I'm up here at 10. At -1, I've made it down to 7. 1, 2, 3, 4, 5, 6, 7. At 0, when x is 0, we've made it to 1. I can already see this isn't scaled very well. I can hear Ashley Blake saying it needs to be a little further to the left. Did you hear her? I did. Okay, so 1, -8. 1, 2, 3, 4, 5, 6, 7, 8. Down to here. And 2 all the way down to 20. So to look at this right here, gosh, it doesn't really look like something that's going to form one of those parabolas, but you never know, it just might, and you're maybe not thinking about it the way that I'm thinking about it, because you're used to the parabola I showed you kind of looking like that. What if this parabola looks something like this? But we'll have to deal with that a little bit later. For now, just knowing that it's nonlinear is good enough. We don't even need to know it's quadratic until next week or the week after. Let's move on to example 4, exercise 4. Still in the frame. Okay, so now I've got some varied input values. I'm seeing an increase of 2 everywhere. What's happening with these values? I see a constant change through, again, 5 values with 4 changes going from the first to the last. I'm seeing a constant rate of change. The change in y over the change in x. Now, one of the things that I told you about writing a rule for a function was that we need to know 2 things. To write the rule, if you can't see this on camera, you have this in your notes. You need to know 2 things. You need to know the rate of change, and you need to know the input value of 0. What output value does it correspond to? What is the output when input equals 0. Now I happen to know it, 3. So I happen to know that the equation of this line is y equals 1/2 x plus 3. And if you test that for any point that we know about this function, we're going to know that it works. Plug in a 4. Half of 4 is 2 plus 3 is 5. So not only can we use the rate of change to know that the next point will be 6 comma 6, an increase of 2 and an increase of 1, we could plug in the 6. Half of 6 is 3 plus 3 will be 6. So we can use this rule to predict anything. If we needed to know what is the input or what is the output when x equals 100. Well, that just means I need to take this value, plug it in here, and I'll say, okay, the output y will equal 1/2 of 100 plus 3, which is 53. So in one way, I could keep using the rate of change to keep generating more and more ordered pairs for the line, or I can use the rule, which is the real value of it, to be able to not only make a prediction, know exactly what it's going to be. So let's look at the fifth exercise. So this guy, -6 to 3, that's an increase of what, plus 9? And then I have going from 3 to 6, that's only an increase of 3. So all of a sudden I see this is not like the other ones where I had a constant increase in inputs. This does not mean it's not linear. We don't know enough yet. So going from 6 to 21, what is that, plus 15? And going from 21 to 30, plus 9 a second time. So I have 3 different increases in x for the 4 different changes. Can't say anything about anything until I know what the change in the outputs are. So going from -8 to -2, that's an increase of 6. I again see, as I did in the last one and several other ones, that as x increases, y also increases. So going from -2 to 0 is a plus 2. Going from 0 to 10, plus 10. And going from this value to this value, recall that this change was plus 9, this change was plus 9. So for this thing to have any chance at all being linear without me thinking about it, this had better be plus 6, the same as I got when the change was 9 before. And looky-loo it is. So I've got a good feeling about this being linear. We'll examine the delta y over delta x for each thing. So 6 over 9, not a simplified fraction. 2 over 3. I'm asking the question, are these equal? Well, these are certainly equal. If I reduce 6 over 9, I get 2/3. But is that equal to 10 over 15? Sure as heck is. And that, as we've already seen, the last one was the same as the first one, 6 over 9. Now, whenever I'm writing rate of change, I see that all of these things check out. They're all equal to the simplified ratio, 2/3. Now I need to write the rule for this just because I want to. Notice that I was not given what I was given in the last one, where I needed to know what the output was when the input was 0. I just look at the table and I got it for free. I don't see the input of 0 here. Now I see an input or an output of 0, but that's not what I need. I need the output when the input is 0. So I need to know, if I input 0 into this function, what do I get? So kind of like I was saying in the last one, where I can count from one step to the next, I need to kind of count, gosh, I don't know, kind of in between these two values. Now the rate of change says that whenever x increases by 3, y increases by 2. So I see here, to kind of blow this part out, I have the point 3 comma -2. Now, as x increases by 3, y is to increase by 2. So I'm thinking backwards here. So I'm subtracting. Here, to go from -6 to +3, I added 9. Now I'm trying to go backwards, so I need to subtract 3. If the rate of change was an increase in 3, I'm trying to go back. So that gets me to my 0. Now I need to know, what was that output? Well, again, I'm going backwards. Usually as x gets bigger, y gets bigger. So as x gets smaller, y gets smaller. So my output when the input is 0, -4. So I know my rate of change. I know my output when the input is 0. So I know my function is equal to y equals 2/3 x minus 4. To check your answers with these kind of things are real nice because you can just pick any of the points that you know, see if it works. Now, I love working with 0. Why don't we plug in 0 for y, or plug in 6 for x, and see if we get the other thing. You could go either way. Plug in the 0 for y. So 0 equals 2/3x minus 4. Add 4 to both sides. 2/3 x. Sounds like we're going to need to multiply both sides by 3/2. We're going to see this cross cancel. And I get the 6 equal to x. If I went the other way and said, let's plug in the 6 for x, and I don't know what y is. So y equals 2/3 times 6 minus 4. Again, some cross cancel action here. So I get 2 times 2, 4 minus 4 to get the 0. So knowing all the points that you do, when you give an answer for what the rule is, real easy to check it. Okay, so let's take another break. We'll come back.